So, welcome to the third targeted proteomics course that we have here in Zurich. So, my name is Christina, or better Tina Ludwig, and currently I'm still a postdoc in the group of Rudy Abersold, but actually this is my last working week here in Zurich. A pretty stressful last working week. And from the 1st of July, I will start my new position at the Technical University in Munich, where I will be heading a new mass spectrometric facility. So maybe I see some of you in Munich then at one point. So the aim of this very first introductory lecture here of the course is to discuss with you the most important basic principles of targeted proteomics in general and of selected reaction monitoring in particular. And as we have just seen from your raising your hands, we are a very heterogeneous group of people here coming from different fields and with different prior knowledge. So, but still, I think in order to bring everybody to the same page, such an introductory lecture is important. But I would like to already apologize for all of those here in the audience who maybe have heard about these principles before or know all about it. But I still hope that you can maybe benefit from yet another wrap-up of all the most important facts. Okay, so I have structured this lecture into 3 different parts. And each part is headlined by a specific fundamental question regarding targeted proteomics and SRM. So in the first part, I would like to discuss with you what actually SRM is, how does it work, and why is it useful. Then in the second part, I would like to design with you a first targeted proteomic experiment, what's important to consider here. And in the last part, we will look at some real SRM data and just that you get a feeling how the data really looks like that you get back from your mass spectrometer. And whenever there are questions arising, really don't hesitate and just interrupt me anytime. Good, so let's start with the first part. And as Rudy already pointed out, the term targeted proteomics does actually not, or in our days, no longer refer just to a single mass spectrometric technique. But there are actually several techniques. And the technique that is the most established and therefore most frequently used technique in the field is selected reaction monitoring, SRM. However, especially in the last years, by using high mass accuracy, high resolution mass spectrometers, also novel approaches have been developed, like parallel reaction monitoring, as well as swath MS. And yeah, as you have heard, now, today, we will mainly focus on SRM, but you will hear a lot about these lectures, and you will get introductory lectures also throughout the week. So what's very confusing on this slide for many people who are new in the field, and honestly also for people like me who are old in the field, is the fact that there exists a range of different names that refer to exactly the same technologies here. So for example, in the literature, you will also find the term multiple reaction monitoring for SRM. And both of these techniques refer to exactly the same technology, the same thing. The same is true for PRM. So PRM sometimes people also call MRM high resolution, MRM-HR, or they talk about pseudo-SRM or pseudo-MRM. And also the swath MS technique has already various different names. So hyperreaction monitoring is one term that was coined and that is used. And very frequently you will also find the term data independent acquisition, DIA, in the literature. And this is of course not desirable to have this mess of namings floating around. And the main reason that causes these different namings is often that different vendors of mass spectrometers trademark their specific name. So I'm afraid also in the future we will have to live with these different naming conventions, and it's just important that all of you are now aware of this issue and that you know what are the differences and what are the commonalities between them. But what's very easy to keep in mind is that no matter which of these targeted techniques you work with in the end, and Rudy pointed this out already, the benefit from all of them is always the same. And what's this benefit? Well, shotgun or discovery proteomics is always the method of choice if you want to globally map out a protein content in a sample. So whenever you want to identify as many proteins or PTMs in your sample, then shotgun proteomics or discovery proteomics is the technique of choice for you. And in the moment when you're not so much interested in identification, but when your target is to do protein quantification, then targeted proteomics might be the ideal technique, as with any of these techniques I just showed you on the slide before, you can generate higher quality quantitative data that is more consistent and more reproducible and more precise and accurate than what you can generate with these shotgun data typically. And I think Rudy, showed this already. Great, very, very great in his presentation. And the reason, or the fact that more and more people also acknowledge or recognize these advantages of targeted proteomics, you can also see from the fact that it was selected as a method of the year in 2012 by Nature Methods. Okay, so now let's go a bit more into the technical details, and let's see how does SRM really work in detail. So what you see here is the standard proteomic workflow. You've seen this many times before, where you always start from some type of protein sample from which you extract the proteins, you digest them, and these complex peptide mixtures you separate, typically at least by doing an HPLC chromatography, and then you need to ionize your peptides before they finally enter the mass spectrometer. And this whole workflow is always exactly the same in every bottom-up mass spectrometric workflow, no matter whether you do discovery or targeted proteomics. The difference really only arises at the last step, namely at the step of the mass spectrometry. And in an SRM experiment, the mass spectrometer that you work with is a so-called triple quadrupole mass spectrometer. And as this name already suggests, triple quadrupole mass spectrometers are built out of 3 quadrupole mass analyzers that are all used in a row. In the first and in the third quadrupole, these two both serve as mass filters, while the second quadrupole serves as the collision cell. So when you have now a mixture of peptides co-eluting from your HPLC system, this mixture of peptides will enter your triple quadrupole, and then ideally here in this first mass filter, only one specific peptide out of this mixture should be selected. So only one peptide will be able to pass this quadrupole, all the others will be filtered out to the side. Then this specific peptide will get fragmented in the second quadrupole, and then again in the third quadrupole, you will only select one out of these several formed fragment ions. And what you will record in an SRM measurement in the end is simply the intensity of this selected fragment ion over time. And that's this chromatographic trace that you will record, and it's this SRM trace that you will use to identify and also to quantify your peptides then in the end. So the unit that is measured in every SRM measurement is always a pair of a peptide precursor that was selected in the first quadrupole and the corresponding selected fragment ion that was selected in the third quadrupole. So we are always measuring Q1, Q3 pairs. And there's a scientific expression for such a Q1, Q3 pair that I will use very frequently throughout the rest of the presentation, and you will hear often throughout the rest of the week. And this term is a transition. So you must know a transition in the context of targeted proteomics is always a Q1, Q3 pair, a peptide and a corresponding fragment. So what are the advantages of working with such triple quadrupole mass spectrometers? Well, due to these 2 filtering steps that you have here in Q1 and in Q3, you can very efficiently reduce noise in your measurements. And this is one reason why SRM measurements are highly, highly sensitive. You can just get rid of a lot of your background noise in the sample. Then quadrupole mass analyzers have a very high ion transmission efficiency. So 95% of this selected peptide precursor ion and this selected fragment ion will actually manage to pass through this quadrupole when you filter for them. And you can very rapidly switch between transitions. You can change the settings and select here different precursors and different fragment ions. And this is why you can do this multiplexing in your SRM measurement. However, there are also disadvantages working with triple quads, and the first big disadvantage is that a quadrupole mass analyzer has a rather low resolution, especially compared to the recent high mass accuracy, high resolution instruments. And this low resolution will always lead to interferences that you will see in your signals that you might not see on instruments with high resolution, or that you might see in PRM mode. And then there is the second disadvantage, and that's that in order to perform an SRM measurement, you need to know what to look for in advance. That means you need to tell the instrument exactly those masses that it should filter for in Q1 and Q3. Okay, so let's have a look at a specific example and see how one would measure this with SRM. So let's assume we're interested in measuring this peptide up here, and you see indicated the B and Y ion fragment series for this peptide. If we want to measure this peptide now with SRM, what we need to provide to the instrument is a table. And this table must have several columns. So the first information that you must provide the instrument is this Q1 value. So that's the precursor mass to charge ratio that you need to tell the instrument that this specific peptide has. And as peptides can be doubly or triply or quadruply charged, you need to know in advance what is the major charge state of this peptide, this target peptide. Then you also need to provide the fragment ions that you're interested in. So in this example, we have selected Y5, 7, 8, and 10, and these are the corresponding mass to charge ratios again. And then there are two additional columns that you always need to tell the instrument to do an SRM experiment, and this is the column of collision energy. That's the energy that you want to apply in the second quadrupole to fragment the peptide. And that's this column here of dwell time. So sometimes also this column is called accumulation or acquisition time. It all refers to the same thing. And this dwell time is the time that you would like to provide to the instrument so that it can accumulate the signal for a specific transition, for a specific fragment. And the more time you give the instrument, the better the instrument will be able to differentiate a true signal from the noise. So the more clean your signal will become. Ideally, you want like to have long dwell times here. So and if you now just generate such a table and you paste it into your mass spectrometer and you press the start button, what will happen is that the instrument will go to the first line of the table that you provided. It will set Q1 and Q3 according to those two values that you give. And then it will acquire intensity for this specific transition for 250 milliseconds. So it will wait 250 milliseconds and record one intensity value for exactly this setup. When this is done, it will switch to the next line of your table, and it will do the same. It will wait 250 milliseconds and record an intensity value for that transition. And it will go through the third line. And like this, it will once go through the whole table that you provide. And once it reaches the last line in your table, it will simply jump back and do the same over and over and over again, over the whole HPLC gradient that you apply. And the data that will come out, if you're lucky, might look like this, where you see now a record of those 4 transitions. You can see that all of those 4 transitions have exactly the same peak shape and the same retention time, and that's actually one very important first requirement. As all of those transitions originate from the same peptide, they should all have exactly the same chromatography, and that's exactly what you see here. However, you do see that there are differences in intensity of these different SRM traces, and that just reflects the different fragmentation pattern, right, that we also know from our MS2 spectra, that different fragments are formed with different intensities, and that's exactly what you see here. However, so actually in reality, these very smooth lines that you see here is not what is recorded by the instrument. These are already extrapolated lines by the analysis software. What the instrument really records, as I just told you, are distinct intensity values. So in reality, the data looks like this. It's only points over time, and the software then extrapolates these lines. And actually, there is one very important parameter, and that's the time differences between 2 of these neighboring points. Because actually, and this time difference is called the cycle time. And this time difference actually gets defined by the number of lines in your table and by the dwell time that you define here. So in this very little artificial example that I show you here, we have only 4 transitions, and we have 250 milliseconds each. So the instrument needs 1 second to once measure through this whole list until it can go back to the top and do it again. So the time difference between each of these points will always be 1 second. Okay? And this cycle time, so this time difference, is actually absolutely important because this time difference will define the quality of your chromatographic trace and how well you can, or an algorithm can, extrapolate the true peak shape. And this is important for SRM, but also for PRM, also for SWOT. No matter what type of chromatographic-based quantification you will do, this will always come back to you, and it's very important that you understand it. And this here is a figure that nicely demonstrates these differences, what happens to the peak when you work with different dwell and cycle times. It's taken from a 2008. So what you see here is in black the theoretical chromatographic trace of a transition. And then you see how this trace was recorded with different dwell and cycle time. So let's first have a look at this purple line. So this purple line was recorded with a very long dwell time of 500 milliseconds, but also with a very long cycle time of only 20 seconds. That means only every 20 seconds the instrument will record a value for this specific transition. And if you have now a peak that is in the range of 30 seconds, half a minute peak width, you will only end up with 2 data points over this whole illusion profile. And by looking at this purple peak, I think you can immediately see that no algorithm in the world will be able to extrapolate the true peak shape from such a measurement. If you halven the cycle time by a factor of 2, so with 10 seconds, you end up with maybe 3 to 4 peaks over the illusion profile. It's still very poor peak shape. And only when you're back in the range of 2 second cycle time, you actually get close to the true picture. And the difference between the blue and the green line here is the dwell time. So if you work with a very short dwell time of 5 milliseconds, so if you only give very short time to the instrument to accumulate signal, the curve is much more spiky. So you will get a much more noisy signal than when you use 50 milliseconds, and then you're really very close to the true peak shape. Okay, so this rather detailed explanation about cycle time and dwell time and how they all are dependent on each other, I did because I hope that now it becomes very clear that every targeted method design is a balancing act between 3 parameters, between dwell time, cycle time, and the number of peptides and transitions and proteins that you can measure. And the goal that you always want to achieve is that you want to be really sensitive, right? You want to measure also low abundant proteins in your sample. And if you want to be sensitive, you need a long dwell time because you need to give the instrument time to separate true signal from noise. And the rule of thumb, what people often work with in the field of SRM, but also in others, is to work with dwell times in the range of 50 to 100 milliseconds. So if you are interested in measuring metabolic proteins that are very abundant in the sample, you can maybe live with only a 5 milliseconds dwell time. But if you are interested in kinases and very low abundant proteins, you must work with longer dwell times and give the instrument more time here. And 100 milliseconds is the higher end of the scale that people typically work with. Then, next to sensitivity, you also want to be quantitatively accurate. You want to have the true peak shape of your chromatographic trace. And for that, you need short cycle times. And again, the rule of thumb, what people try to do here is they try to work with at least 8 to 10 data points over your illusion profile. And in fact, this often means that you need to work with cycle times in the range between 1.5 and 4 seconds. Which cycle time is appropriate for you personally will, of course, depend on your LC system, right? Because your LC system will define what is your average peak width. And the broader the peaks, the longer cycle times you can still live with, the shorter, the more narrow your average peak width, the faster your cycle time will have to be as well. And this is just something that everybody who's working with these mass spectrometers will have to figure out and investigate themselves. What's the ideal cycle time on your instrument, in your LC setup. And then there is this final point on the wish list. Very often what we want to measure are many proteins with several peptides per proteins and several transitions per peptide. And the rules of thumb that here often people apply is that if you're interested in measuring a protein, always try to work with several peptides per protein. Don't target just a single peptide per protein, but several. Maybe 3 to 5 is what most people try to do. And every peptide measure with several transitions, with 4 to 6 is what we usually work with in the lab. And the maximum number of transitions that can be routinely and with a reasonable accuracy measured in one SRM injection is in the range of 1,000 transitions. So this table that I showed you before can at maximum have a number of rows of 1,000. However, even this 1,000 transitions can only be achieved with a specific trick, and this trick is called retention time scheduling. Has anybody of you never heard about retention time scheduling? So you all know, yeah? Not really? So then I quickly explain it once more. So what retention time scheduling means is that you do not monitor the transitions of a specific peptide over the whole LC gradient that you apply, but you just define your acquisition to a certain retention time window where you expect your peptide to elute. So if we are having here this example, 4 different peptides that are eluting at 4 different retention times, what you would do is you would measure the transitions for peptide 1 only from 8 to 18 minutes, and the transitions for peptide 2 only from 18 to 30 minutes, and so on and so forth. And like this, you can reduce the number of transitions per segment, and therefore improve on your cycle and your dwell time, for example. Or you can just add more peptides in this specific segment. So scheduled SRM can help to increase the number of transitions by a factor of 5 to 20-fold. The narrower you make the segments about the peptide, the bigger the positive benefit of such scheduling will be, but the bigger the risk that your peptide might shift out of your specific retention time window completely, and you will end up with no valuable measurement at all. But one very important requirement, if you want to use such scheduling, and we in the lab, for example, use retention time scheduling for every SRM measurement that we do. Once you have done it, you definitely don't want to miss it, and you will do it regularly. And if you want to do this, you need to have accurate retention time information up front, right? You need to have this information available. Okay, so just to quickly summarize once more the performance profile of SRM. So the advantages of SRM are shown here in this green box. So SRM is the ideal technique if you want to monitor the abundance of a set of predefined target proteins or predefined PTMs, and if you want to do this over many samples. The SRM has a very wide dynamic quantification range, so you can quantify in one measurement proteins that have abundance difference in the range of 4 to 5 orders of magnitude. And this is one of the biggest dynamic quantification ranges that you can span in mass spectrometry by using this SRM technique. Further, SRM is very reproducible and repeatable, as Rudy has also shown you based on some data already. And the big advantage with SRM is that's already well supported by public resources, so there are several software tools, there are spectral repositories available, and with maybe some of the more recent technologies in targeted proteomics, this support is still a little bit less well than it is with SRM. However, there are also disadvantages. So as we already said, in order to perform an SRM experiment, you need to have prior knowledge about all your target proteins or all your target PTMs. And this prior knowledge is gathered in what we call an SRM assay, and we will in the next part discuss in more detail how this SRM assay looks like. The second disadvantage of SRM is the rather low resolution of the triple quad instruments, leading to more issues with interferences in your quantitative data. And this limited multiplexing capacity, so the number of transitions to be measured per SRM injection is in the range of 1,000, and especially in the light of these last limitations, these new techniques, PRM and SWOT-MS, were really pushed to help to improve this. Okay, so in order to wrap up, or to just summarize once more this first part, I would like to once more illustrate the differences between different mass spectrometric techniques in a very, let's say, easy to remember, but also very simplified analogy. And that's the analogy of exploring a new city. So let's assume you would like to explore Zurich for the first time in your life. The shotgun way of exploring Zurich would be to take a look at the skyline of Zurich and to very specifically select all the most intense, tallest buildings in Zurich, and you would visit, or during your stay in Zurich, all these tallest buildings. And the assumption behind this would be that these tallest buildings are actually the most important and most informative and nicest buildings of Zurich. And actually this might be true for some of them, but you can also see that with such an approach of always just looking at the tallest things, you might lose some very interesting aspects of Zurich that are still very worth a visit. If you would do the SRM way of sightseeing Zurich, the approach would be very different. So in this case, you would first, before you start your travel, you would sit down at home and you would read this Zurich City Guidebook. And based on what you read there, you would decide, okay, this and this and these are the interesting things for me personally to see while I'm in Zurich. And then we are in the city. You would visit all those specific places, and they can, of course, include these tall buildings that you have seen before with shotgun, like the beautiful Prime Tower or the Uetliberg, but you can also include the small things in your visit, which you would have missed with a shotgun approach. And finally, a data-independent acquisition or SWOS way of sightseeing Zurich would be that you would come into Zurich and you would start photographing everything. Every house, every person, every street, everything. It would be a very, very stressful visit. And only when you're back home, you would start taking a city guidebook of Zurich, and you would, based on what you read there and based on all the pictures that you have taken, you would decide, okay, well, these are the most interesting places actually, and these are what I would like to show my friends and my parents. And as you have photographed everything, you will have the tall buildings in there, but you will also have the small things of the city included in your data. So that's one way of keeping in mind and understanding the differences between these different approaches. Okay, so are there any more questions to this first part, how SRM works, why is it useful, and what are the details? Okay, if not, then we go to the second part. So how do I design a targeted proteomic experiment? So what do you need to do now if you want to do for the first time your own SRM measurement on your proteins of interest? So what you need to perform an SRM experiment is you need information, 3 different types of information. First, you need to know exactly which proteins you would like to target, or which PTMs. Then, for every protein, you need to select a few best representative peptides per protein. And once you know which should be the representative peptides per protein, you must select for each peptide the optimal transitions that you want to target in your transition list. And we will go through these 3 different types of information now, and I will give you some tips and tricks how you do this selection or what you can do here. Okay, let's start with the protein selection. So the protein selection obviously depends on each project and each study. You can mine the literature for interesting proteins. You can use any type of experimental data to define target proteins. So actually there's not much I can tell you, as this really depends on each individual person and each individual project. However, what's maybe good to keep in mind is the number of proteins that you can target with these 3 different approaches. So a good project for an SRM study are projects that involve 10 to maximally maybe 100 proteins. That's are the ideal projects for SRM. With PRM, you can increase this number maybe to a few hundreds. It's still reasonably manageable with PRM, while when you want to target thousands of proteins, the SWOS technology is the only targeted technique where you can do this, let's say, in a reasonable effort and time frame. Okay, so let's assume we now have a list of target proteins. Next, we want to select now the optimal peptides for these target proteins. And when we work with trypsin, but also with most other proteases, each protein typically yields tens to hundreds of different peptides. And what we want to do in our SRM analysis, we want to select really just a handful of those, because you've just heard, we have this list of 1,000 transitions. That's the maximum we can do. We don't want to spend 1,000 transitions on just a single protein. And the big question is, which ones shall we take? And what people do in the literature to select these peptides is they select peptides that fulfill 2 criteria. The first one is they want to try to select those peptides that are the best flying, mass spectrometrically best flying peptides. So the most intense peptides that a protein forms, because then you can be maximally sensitive. When you select those ones, they will give you the highest signal. You will be maximally sensitive in your measurement. And then they also try to select those peptides that are unique for a given protein within a proteome, because then you will be always selective for this one target protein that you are interested in. So how do you find out which are now these best flying peptides in your sample? Well, the best way to find out which are these best flying peptides is to use empirical data. And there are 2 different sources of empirical data. You can either use the data of other people, and there are a lot of public data repositories out there where proteomic data is stored, like the Peptide Atlas or PRIDE or Proteomics DB and many others. And you can mine those databases and look which peptides for my protein has been identified by others before. Or you can say, okay, I don't trust in the data of others, I produce my own empirical data. And one thing what typically people do is they perform proteome mapping experiments, so they do shotgun analysis on their own samples of interest and see which peptides can I identify, and they use this then for SRM. If you want to increase the coverage of peptides for protein or measure even proteins that might not be identified in these initial shotgun survey scans, then what you can do is you can fractionate your samples of interest before you do the shotgun. So what we here in the aerosol group do often is isoelectric focusing by off-gel electrophoresis, but you can also do any other type of peptide fragmentation. Or you can in vitro synthesize your proteins and thereby produce a proteomic sample where your target protein is of very high abundance. Or one last option is you can simply select every peptide per protein that is theoretically digested, that is when you do in silico digestion that is produced, and then try to target all of them in a survey analysis with SRM, and then you pick which are the best ones there. This is of course very time consuming, and this is why you can only follow this approach if you have really very few protein targets you're interested in. And in case there's absolutely no empirical data out there at all and you have no chance to produce some yourself, the second option that you have to find the best flying peptides is to use prediction. So to use computational prediction tools. There are several out there. One, for example, is called peptide sieve, and these are just tools that based on the protein amino acid sequence can predict which peptides will most likely be the best flyers. However, this approach is definitely less successful in really finding the best ones than when you use empirical data. So it's always better to use empirical data, but still this is a valuable option if you don't have this empirical data. And there is, again, a scientific expression for peptides that fulfill these two criteria, and this is because these peptides are also called proteotypic peptides. In the last few years, there is actually a second term coined by the field, and maybe some of you have heard this already, and that's called a quantotypic peptide. Does any one of you know what a quantotypic peptide is? So a quantotypic peptide, so every quantotypic peptide will also be a proteotypic peptide, but additionally, quantotypic peptides fulfill a few more criteria that make these peptides optimally suited for protein quantification. So these additional criteria are shown here. So for example, a quantotypic peptide should be a peptide that gets completely and reproducibly cleaved from its mother protein. So when you work with trypsinates, for example, you should, for example, avoid working with miscleaved or partly tryptic peptides, as you're never sure how much of these peptides is miscleaved and how much not when you do quantification. You should also avoid tryptic peptides with two neighboring basic amino acids, so these KK, RR, KRRK sequences at either the N or the C terminal end of your peptides. You should also avoid acidic residues close to the cleavage site, so aspartic acid or glutamic acid, as it's known that trypsin does a bad job if these negatively charged amino acids are close to the cleavage site. And you should also avoid peptides that have a KP or RP sequence. So typically we always assume that KP and RP are not cleaved by trypsin, but it has been shown that actually sometimes trypsin does cleave these sequences. So ideally also try to avoid them. Then there is the second criteria of quantotypic peptides, and that means quantotypic peptides should not be prone to chemical modifications. So for example, tryptophan and methionine amino acids are prone to oxidation. Try to avoid those. NG, QG sequences are prone to deamidation. Try to avoid these ones. N-terminal cyclization can happen on QE and carbamidulated N-terminal cysteine residues. Try to avoid those as well. And then there is this last big field of criteria of quantotypic peptides, and that's avoid peptides that carry a biological modification, so any types of PTMs. And this, I think, is even the most difficult part to fulfill, because you never know which ones might be modified and which ones not. The only thing that you can do is you can, for example, check online repositories for PTMs, or you can try to avoid known PTM motifs, such as the NXST motif of glycosylation. And you can also try to avoid very N and C terminal peptides of your proteins, as they are known to be degraded or known to be chopped off by proteases. So the reality is now that all of these criteria are, of course, very valid, and they all are true, and if you can follow all of them, they will help to improve your quantitation. However, if you really follow all of them, what's happening in reality that very often you will not end up with a single suitable peptide per protein that is detectable by mass spectrometry. So what people do is they try to relax, or they start to relax on some of these criteria. And just one more comment that I would like to make here, and I will come back to this tomorrow in the second presentation, is that especially these first two criteria here of complete proteolysis and chemical modifications, these 2 points are very important if you do absolute quantification. Because it is true that any of variation here, when you don't cleave a protein completely or when you have a chemical modification, this will immediately affect your absolute protein quantification. However, if you do relative protein quantification, and the vast majority of us is doing this, and if you can ensure that incomplete proteolysis is reproducible over all the samples that you would like to relatively compare, same with oxidation of methanions due to sample handling, if it's reproducible over all the samples that you want to compare, this will not affect your relative protein quantification. So this might help you to relax on some of these criteria without feeling too bad about it. Okay. So let's assume now we have selected, using these approaches, quantotypic or proteotypic peptides for all the proteins. The last piece of information that is missing are now the optimal transitions per peptide. So again, each peptide that we have selected can produce a series of fragment ions, not only Y and B ions, but also A, Z, X, Z ions, water loss ions, amine loss ions. And very easily, when you sum all of those up, you end up with 50, 100, or 200 transitions per peptide. And we don't have the time to measure them all. So we again want to select only a few ones. And the way how people select those transitions is actually very similar how they select already the peptides. It's exactly the same rules that apply. So typically we try to always select the most intense transitions per peptide to be really sensitive. And we would like to select a unique transition signature. So the combinations of transitions that you work with should be unique for your peptide of interest, because only then you're selective for your peptides. And how do you find out to which transitions these 2 rules apply? Well, ideally use empirical data. Again, there are public repositories, so you can use exactly the same repositories I just showed you before on peptide level. As long as you have MS2 spectra information provided in these libraries, you can use these MS2 spectra to select the most intense transitions. And additionally, there are also, especially in the last years, there are new public repositories developing specific for targeted proteomics, like the SRM Atlas or SWOT Atlas or Panorama, where you can directly download transition lists and use it for your own data. Or do your own personal measurements to find out which are the best transitions. And for this purpose, you can use any type of mass spectrometric approach that generates MS2 spectra for you that you can search and identify. You can use shotgun, but you can do also other measurement modes, like, for example, SRM triggered MS2 or parallel reaction monitoring. And the beauty of SRM triggered MS2 is that you can perform it on exactly the same instrument as you do the SRM measurements on later on. So you will make sure that you have the same fragmentation pattern. And these type of MS2 generating measurements you can do either on your samples of interest, or to increase the chance of getting a high quality MS2 spectra, you can also do it with synthetic peptides. And here the big advantage is that these synthetic peptides do not need to be very pure, because they only need to trigger an MS2 spectra. It doesn't matter if they are dirty, and therefore you can use really cheap peptides, and usually they're in the range of 7 to 10 euros only. Or you can use these in vitro synthesized proteins, or again, you have the option of just selecting all transitions per peptide. Typically what the people do is the Y-ion series, do one survey measurement, and then figure out by SRM which are the best ones to work with in the future. But this is time consuming and usually just doable with a few peptide targets. And also for transition selection, there are computational algorithms around. So here I have listed 3 examples from the literature that you can use to predict, based on a peptide amino acid sequence, the most intense transitions. Yeah?
Sorry, for your own data, there was a discussion or maybe some hints in the literature that maybe HCD data are more suited to predict best transitions than CID data. Do you have any experience on that?
Well, so we didn't do a big survey of this ourselves. it's just from, let's say, not a complete comprehensive study on that, but I know the paper and I just know it from own experiments. This is definitely true. So in HCD mode, if you generate data on an Orbitrap in HCD mode and you want to use it for your SRM measurements on a triple quad, you get a better fragmentation similarity. But also Arjo will come back to this and explain a bit this afternoon in his lecture. You will hear more about that. Any more questions? Good, so then let me wrap up this part. So what I've shown you on all the slides before is that in order to do an SRM measurement, you actually need to have prior knowledge on all the steps of the proteomic workflow. You need to know which proteins you would like to target, you need to know which are the proteotypic or quantotypic peptide you're interested in, and you need to know how these peptides then behave on your mass spectrometer, what's the precursor M/Z value, the fragment, which collision energy do you want to use, and at the specific collision energy, how do these fragments then look like. And all of those indicated parameters are really strictly required for every SRM measurement. So these information you need to have before you can press the start button on an SRM instrument. However, there are even additional parameters that we also store in our targeted proteomic assays and that are not strictly required, but they're optional, but highly useful. And these additional parameters are, for example, the chromatographic retention time of the peptide. And actually, this parameter does become strictly required if you want to do scheduled SRM. However, it's not necessary before data acquisition if you do non-scheduled SRM, but in any case, it's always a very, very important parameter for targeted data analysis. And you will also hear this a lot more once you come to swath data analysis later on. And then there is this fifth additional parameter, and these are the relative transition intensities. So we store in our targeted assays also the information about which is the most intense formed fragment, what's the second most intense, and what's the relative intensity between these transitions. And again, this is information that is not needed before the data acquisition, but it's very useful information afterwards for the targeted data analysis, and you will see this more. So, and this really, the sum of all those parameters is what we call in the end an SRM or targeted proteomic assay. And the way you save all this information is simply in form of a large table with a lot of columns. This is how these things are saved and distributed, and how you can download them from the internet and from websites and use this information. And this table contains, once more, the proteins, the peptide sequences. In all these columns, you have defined how this peptide behaves on the mass spectrometer. We have the dwell time and the collision energy, which we already discussed. And the last column here is once more the peptide retention time. And here I just would like to very quickly add, because Arjo will explain a lot more about this this afternoon, but this peptide retention time that we store here in these targeted proteomic assays is not a real retention time in the unit like minutes or seconds, because of course peptide retention times very much depend on your LC setup, on the length of your column, on the age of your column, and a lot of different parameters. So it does not make sense to distribute or to store here this setup-dependent retention times. And what we do instead is we store here normalized peptide retention times. We call this also the IRT retention time. And that's a retention time that is unit-free and that you can use to share your retention time information. And Arjo will explain you how this works in detail. And what's very apparent from this big list is that generating these optimal and validated targeted assays is quite work and cost intensive. So in my own experience with all the SRM projects that I worked on, I spent much more time on this assay optimization and validation than on the final quantitative measurements on my samples of interest. However, the good news is that once developed, targeted assays can be used universally and they can be stored in public repositories. So in other words, you can benefit from work other people have spent into generating their targets, and if you provide your assays on public repositories, also other people can benefit from your work. And there are several of these targeted assay repositories out there. Here you find all the links to them, and I can just encourage you to really go to these websites, and when you start doing SRM, check out what other people have done on your target proteins, and also donate your own data to these web portals and to make it a community effort, this targeted assay design. With this, I'm at the third part of the presentation. Are there any more questions to targeted assay design? Yeah. Mm-hmm. Well, it's a very good question, and actually I removed this slide from here. Usually it was always on there. So there are different ways to define uniqueness, obviously, and the way how they do it, they just take the protein sequence of a whole proteome, right? Take the gene and they translate it. They take all the open reading frames. This is what they use as the protein sequence, and they just search peptide uniqueness according to this. And for many cases, this might be also okay. However, in the moment when you want to be able to differentiate splice isoforms in human or SNPs in human, then you will have to define peptide uniqueness taking into account exactly these things. And you have also on NCBI, you have these bigger protein databases out, and then you will have to work with those ones. So it's very important that you yourself need to define in the very beginning, do I want to differentiate between isoforms, or is it for me absolutely okay to just report the quantity of a group of isoform proteins, which might be also still very, very okay. It depends on the initial question.
Yeah, this is clear, but let's say you want a separate isoform.
Mm-hmm.
Is there sort of a website or a repository where you can bulk import a whole peptide list and then you get...
So, I mean, I'm not an expert in that. Maybe somebody else even knows more. But I think I thought usually it's mainly on NCBI, where at least for human, you have these canonical and non-canonical sequences to download. How true they are, how complete they are, no clue. But you find for human these things. For non-human, and the problem is...
Practical terms in Skyline, right, there's a function for this. Is that what you're asking for? Yeah. So that in Skyline supports this importing the fast day and then having a set of peptides and then check the uniqueness against the... Okay.
Exactly, but it will depend on the FASTA file. And there are different FASTA files. There are the ones that have this included and not. And you must make sure you work with the right FASTA file for you. Yeah? Well, I mean, this is distinguished based on the FASTA file, based on the sequence. So, yeah, but I mean, we are talking about this. This might be a bigger issue in discovery. But usually with targeted proteomic data, you would not be able to distinguish anyway. It's just that you know based on the FASTA file whether it was the one or the other, and you assume that. Based on the data, you cannot distinguish between it.
Yeah, but then in my blast, I should replace all the I's with L's and do all combinations.
Well, but this you would and then need to do already at the discovery phase, right? In a way. So this is a general question for discovery proteomics. How much do you trust your DNA sequence of the organism you're working with, and how wrong is it and not, right? But I mean, I can tell you this is definitely usually not what people would do. I mean, usually people would just assume the FASTA file is correct and the sequence has been assigned correctly, and then you will not have interferences from, because what Jared is saying, that when you have both versions of a peptide available, you might have interferences from that. And this would not, if the FASTA file is correct, then this would not be an issue. Exactly, that then would have an interference, right? That then would have an interference which causes more interferences that you could not predict before or so. We can discuss it also once more in the... Definitely this is not the standard workflow what people would do, but of course you could do this and get an even better feeling of possible interferences, assuming that the underlying background proteome is wrong maybe. Okay, so third part, let's have a look at some real SRM data. So here you see once more all the vendors of triple quadrupole mass spectrometers, like ABSciX, Thermo, Agilent, Waters, Bruker, Shimadzu, that are out there at the moment. And as this is always the case in industry, with each instrument, there usually comes also the own vendor-specific software. And in the past, it has been often, literally impossible to directly compare data coming from these different instruments, as you never know whether the difference that you see is coming actually from the software or from the measurement itself. So when Brandon started his Skyline project, we're actually very happy that this project was designed right from the beginning in a way that it should support any type of mass spectrometric data coming from any of these vendors. So now you're the lucky people who can already benefit from that and work with just one software for any type of different data. Okay, so now let's have a look at how can you now reliably identify a peptide from your SRM data. And there are actually 6 criteria that you can apply in order to make sure that you're really measuring what you think you're measuring. The first criteria we discussed already. So if you measure several transitions for a peptide of interest, then all of those transitions should perfectly coelute because they all originate from the same peptide, so they all should have the same chromatography. As on the column, you still have the peptide unity, right? And in this little example, you see, for example, that this blue transition is clearly shifted in retention time from these other 3 transitions. So this blue transition is clearly what we call then interfered. There's another analyte, another peptide or contaminant in the sample that induces this blue transition. And this is why for accurate quantification, you would actually like to delete this blue transition and just rely your quantification based on the other 3. The second criterion that you can apply is peak shape. So this is an example. It's exactly the same theory. All transitions coming from the same peptide should have the same chromatography. So a peak like this that is actually not perfectly Gaussian is even, for this purpose of SRM, is even nice because I'm even more sure that this non-Gaussian peak shape all these signals come from exactly the same peptide. And then there is the third criterion that you can apply, and that's a signal intensity. So if you work with an optimal validated SRM assay for a specific target peptide, it is, let's say, likely that the most intense signal of coeluting transitions is your peptide of interest. However, with this criterion, you have, of course, to be careful, because if this thing holds true what Rudy just explained before, that you have an interference with an peptide coming from a very abundant protein in your sample and your target protein is actually a very low abundant protein in the sample, it might well be that your target peptide is actually this small guy here at the site and not the most intense peak in the signal. However, by taking the signal intensity or see the signal intensity as the sum of many criterion, it is still often very helpful to also look at the signal intensity. Take it as one rule out of several, not as the exclusive rule. So all of these 3 criteria here can always be applied. You do not need to have any prior knowledge. You can apply these rules just by looking at the data as it comes out of the instrument and as you look at it in Skyline. But unfortunately, very often when you work with complex samples, these 3 criteria are not enough to be really sure that you're looking at the right thing. And this is why it's important to have additional criteria. And one additional criteria is the correlation to a library spectrum. So if you have identified your peptide of interest in an MS2 spectrum, and you used this spectrum to generate your assay, right? Then what you would expect is that the relative intensities that you see here in your SRM peak match the relative intensities, more or less, that you also see in these MS2 spectra. So Y6 is the most intense, the yellow one, and then next comes the purple, and so on and so forth. So that's another criteria that you can apply. Then we have retention time. So when you have retention time information available, when you know where you expect your peptide to elute, and this is indicated here in Skyline with this little yellow shaded box, and this is the precise retention time where you expect your peptide to elute, and you see that the signal that you get is very close to this value, you improve your confidence that you're looking at the right thing. And the third and most important criterion that you can apply is using a heavy labeled reference molecule. And because what you would expect is a perfect correlation between your light endogenous and your heavy reference. So a light SRM trace and a heavy SRM trace should always perfectly match each other in terms of relative transition intensities and also in terms of retention time. Okay, so And now on the last few slides, I would just like to practice these 6 different criteria with you based on some real data. So let's first have a look at a very nice example. So that's data from myself. I think these were measurements done in yeast total cell extracts. I was targeting this peptide here with these 5 different proteins. This is a non-scheduled SRM run, as you can see here, because we have actually signal for these 5 different transitions over the whole gradient, so from 0 up to 45 minutes. That was the gradient length that I applied. And when you look at such a signal, you see that it's just one retention time where all of those 5 transitions are very high intense. They have the same peak shape. They're coeluting. So I can immediately say, just by applying these first 3 criteria, this is my SRM peak, and I will use this for quantification, and I'm done. But unfortunately, so I think this RPS6A is one of the most abundant proteins in yeast. So unfortunately, very rarely SRM data will look so beautiful. Much more often, you will see data that looks like this. So this is another peptide coming from a kinase, and you can see these 5 different transitions were measured. And here now there are actually 2 retention times where I see coelution of these 2 different, of those set of transitions. So 60 minutes or 23 minutes? Who is for 16 minutes? Raise your hands. Cowards. Who is for 23 minutes? Okay, why are you for 23 minutes? You think the peak shape is a bit better? Ah, well, I would say they're very similar, yeah. But I mean, you're all right. There is no way to really be sure about it, right? You pick, and you will never know if you're really measuring the right thing. So what can I do? What should you do now? Look for an MS2 spectra. Luckily, I had an MS2 spectra. And this spectra looks like this. So that was the spectra that I used to generate this assay, and that came from the library. And now you can say, so here in the spectra we see the Y9 is the most intense transition. The Y9 is the purple one. So it looks already immediately here, the purple is the most intense. Here it's even just second most intense one. So looks like most of you were probably right. And actually Skyline has a very fast way of conveying this information to you, how well the spectra matches to the different traces. This is called the dot product. So Skyline will report for you, and you will see this a lot in the next days, a dot product for every peptide. And what this dot product means is it will just make a correlation between the intensities here in the spectra and between the intensities measured here in these 2 SRM traces. The dot product can be between 0 and 1. 1 means perfect match, 0 means no match. And you can see that this dot product of 0.99 fits much better than the dot product here. And so now, by having this additional information of the MS2 spectra, I'm actually very confident that I will use this peak for quantification, and this is my true peptide. Yeah, it's a good point. There is no let's say, threshold everybody agrees on, not at all. And the problem is that also this threshold that you get, or this value, will very much depend on the source of this MS2 library. So this goes into the same direction. Whether you use a library generated in CID mode on an Orbitrap, you must relax. The match will be much worse than when you use a library that was measured in SRM triggered MS2 mode on a triple quad, and then you can really often get dot products in the range of above 0.98. So there is no easy answer to this question, and you must judge it a little bit yourself. I always tell people to look at your data, see things where you're sure they are right, you're sure they are wrong, look what were the dot products, and make a cutoff according to empirical observation. But it depends a lot on the source of this MS2 spectra library. So, but even this example that I showed you here is still a very nice example. It was easily solved. Very often, if you're interested in low abundant proteins, SRM data looks like this. So what's the right peak? No chance to get it here. So let's have a look at the MS2 spectra and look at all the dot products. And even in this case, this dot product analysis didn't help a whole lot because, and that's often actually something that's often happening when you're measuring noise, at least to me. When you have an MS2 spectra with similar intensities of fragments, that's exactly also what you see with noise, similar intensity of all the noise. And then you get very good dot products actually for a lot of these noisy data. So the MS2 spectra in this case didn't help at all to differentiate between these different peaks now. What can we do? Sorry? Retention time? Heavy standard. Both correct, exactly. Retention time or heavy standard. And heavy standard is even the most powerful one that we have, even better than retention time prediction. You always have still some variability. So what I did in this case here, I didn't have a synthetic reference heavy standard to spike in, but I could very easily grow yeast completely 15N labeled. So where you just provide to the growth media 15N labeled ammonium sulfide, and I generated a completely heavy labeled yeast. So this is once more the signal you already know, the light endogenous one, and this is now the heavy labeled one. And then I compared these two. So this is the overlay between heavy and light. And now you just must trust me. There was actually just one retention time, and that's this at 11.8 minutes, where I got perfect correlation between the blue and the light, the heavy and the light curve. And that was this peak here at 11 minutes. And you can see that this peak, even the relative intensities between heavy and light were matching. It's not as beautiful the peak as the peaks I've shown you before, no question. But still, you can see very similar relative intensities. This was one of the dot products with 0.99. And I also had retention times predicted using SSR calc, a general prediction algorithm. And that said it would be at 11 minutes, and I had 11.8. So by using all the 6 criteria, including heavy reference, retention time, MS2 spectra, I could, even though this is a low quality signal, still quite confidently say this is this peptide, and I can quantify it over various samples. But without this additional knowledge, just by looking at intensities and peak shapes, this would have been impossible. And just to be complete, this is an example that also with SRM you will never be able to measure everything. So there will also be cases, even though SRM is a very sensitive technique, where you just see noise in any channel, and you will have to face the truth and say this is not detectable. Okay. Any more questions to this data? Yeah. So I mean, when I do this manual analysis in Skyline, I never do this. One problem is that this intensity threshold, if you apply one, this is very different depending on the retention time you're looking at, right? So at the end of the gradient, you can have very beautifully low, noisy peaks with an intensity of below 1,000 counts per second, while this is completely mass at a retention time of 20 minutes where there are many, many peptides eluting. So the background intensity is very much chromatography dependent. This is why I always had a problem applying something like this. You would need to do it in a retention time defined manner. So usually when I do my manual analysis in Skyline, I would never do this, and I just look at the chromatograms, I go through them, and I decide based on this. But yeah, for a global analysis, this is definitely something to consider and to think about. Yeah, no perfect, easy answer. Okay? Good, so then I just quickly summarize once more what I think are the most important take-home messages from this first presentation. So SRM is the most established technology in the growing field of targeted proteomics. However, it's only one out of several techniques that are out there by now. It's the ideal technique if you want to analyze a set of predefined proteins or predefined PTMs over many samples. If you have a project where this applies, then you should consider SRM as your method of choice. And the advantages that you can expect from your SRM measurements is that you can cover the widest, or one of the widest dynamic quantification ranges, namely 4 to 5 orders of magnitude, which means you will be very sensitive, more sensitive than with many other mass spectrometric techniques, and you will have this high degree of reproducibility and repeatability. Your metrics, this was the picture that Rudy showed, your metrics of data will be more filled than when you work with discovery proteomics. However, the limitations that you always need to consider is you need to have an SRM assay in your hand before you can do the measurement. You will have more issues with interferences than when you do, for example, PRM measurements, as you have the low resolution on the triple quadrupole instruments, and you are limited per SRM injection to this roughly 1,000 transitions. And for confident peptide identification, we just now discussed in detail these 6 criteria that I showed you. coelution, peak shape, and peak intensity that can always be applied. And then these criteria that need prior knowledge, like correlation to an MS2 spectrum, correlation to previous retention time information, and the correlation to a heavy reference. And just the last very important point that now is still missing is actually the question, and how do I quantify now my proteins and peptides in my targeted mass spectrometric measurements? Because actually that's the whole reason why we do this, right? That's the benefit of SRM, is protein quantification. And the answer to that, or I would like to refer, in order to answer this question, to the lecture tomorrow, where we will spend a whole hour just on looking at this point of protein quantification. So thanks a lot for your attention, and if there are any more questions, I'm happy to answer. Yeah? Yeah? Yeah, so we in the lab only use nanoflow and nanocolumns. But we can do SRM measurements, of course, also on micro systems. But I guess most groups, there are the advantages and disadvantages, and I guess most groups do nanospray and nanocolumn and nano HPLC systems. Mm-hmm. No, not at all. I mean, there is actually, there's almost no reason. We will come to this a lot tomorrow in the quantification lecture. But there is no reason not to use a heavy label. It's always beneficial to have a heavy reference peptide, but it's of course expensive, right, to do this. And it is possible to do also label-free quantification with targeted proteomics. You will have certain disadvantages, and we will talk about them tomorrow. And label-free? Yeah, sure. I wouldn't say, there are many papers out who have done this. Of course, you will have disadvantages in terms of run-to-run variations, in terms of higher CVs, and all these things that apply exactly the same way also to shotgun label-free anyway. But there's no reason why you cannot do this in your data. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. It is a very good question, and I will just refer to Ariel. So this afternoon you will have another whole lecture just on how to set up the assays, and then there will come collision energies a lot more, and IRT and retention time prediction. And it's not always the same between all devices, unfortunately. Okay, super. So then we are only 15 minutes late. And I would just say that, but in order to stick to the time, let's meet here again in this room on time, which means you have only 1 hour, 15 minutes lunch break. I hope you will manage to do this in there. Good.
Actually, only 1 hour today.
Today it's only 1. Yeah, so then you will only have 45 minutes. Will you manage, or would you prefer to have everything postponed by 15 minutes? We do only 40, huh? We do an hour. Okay, so then, forget what I said before. In 1 hour, back here.